Everyone, and I welcome you to this session on data science. I know we had a gap of more than a week at least due to my various other commitments. Uh, all right, so slightly, I mean, getting getting some other activities, getting into some other activities, which is what has blocked my last week. And possibly I was telling Ravindra that I will give only a weekly schedule from now onwards because in the future there are a few periods where there is, I mean, the regular schedule may not be adhered to the Monday, Wednesday, and Friday kind of a schedule. So based on my schedule for the coming week, probably on Friday or something, I'll inform Ravindra on the possible dates for the coming week. And accordingly, we will schedule our sessions. I know it's a uncomfort for you, but rather than, some of the unavoidable things, and that's the reason I thought I should prioritize accordingly. I don't know if you people are comfortable in the morning slot, probably let's say from 7 a.m. to 9 a.m. or slightly lesser 7 to 8:30 or 7 to 9 kind of a slot in the morning, provided I miss out on some evenings. So that is one more thing I was thinking of if there is a possibility. But yeah, it can't be just with one person or two. Yeah, so you see, so mornings generally, I mean, though it is very comfortable for me, I'm relatively less loaded in the morning. But again, I'm sure a lot of people would miss out the mornings, right? So I mean, when we announce itself, if we make the morning slot, then it's a different thing. But always it has been our experience. But initially, once we announce in the evening, shifting it to morning would be slightly difficult. So my only request is possibly there could be some on and offs in the regular schedule. Okay. Yeah, but we can't help. I mean, I can't have two different batches for this. So whatever is something that we have announced initially, we will go with that only. And possibly if I take a few Sundays or something, would you be comfortable? Sundays probably a little bit longer on a few Sundays, on one or two Sundays, because even Sundays are generally blocked for me. But in the coming weeks, I see that I can actually take out one or two Sundays. So for whatever we have lost, I can even. Okay, okay. Saturday, I am completely blocked. That's the reason the initial slot that I had, 3:30 to 5:30 on Saturday, somewhere I could not schedule. So yeah, we'll continue then. Possibly, I mean, we'll have to take the opinion of many people, but we'll continue the same way. I'll see if I can take out at least 3 days during the week, right? So that we can plan it accordingly. So yeah, let's ignore everything here. We don't need any further messages. We'll continue with the same weekdays schedule, right? Probably the only thing is I'll see if 3 per week or 4 per week. So every week I'll give a slightly different schedule. That's the only thing I know. I'm slightly deviating from the initial schedule, but it's a humble request. And in case you miss out, I probably request you to go through the videos, because weekdays is what we have planned, and generally we planned it as Monday, Wednesday, Friday, but somewhere because of some cancellations and some other activities coming up in my way, so somewhere we had to adjust. So I'll give you the schedule a week in advance. So it might be possible that if I am free in a particular week, yeah. So no, I mean, it's not about my preparation. Preparation is already done, as you have seen. There's a lot of code that has already been done. So my preparation is done. The only thing is about the class schedule. Okay. So we'll go with 7 to 9 p.m. only. The only thing is the schedule, the days will announce them a week in advance rather than continuous, rather than a fixed 3 days. I'll give you a week's notice so that you can plan your activities accordingly. So Ravindra or myself in the WhatsApp group, I'll post in the WhatsApp group that these are the days I will be comfortable taking in the coming week. I think we'll should stick to that. So for this week, as might have been already communicated by Ravindra, we will be having it on Monday, Tuesday, and Thursday. Right? We'll have the classes on the 3 days for this week, because on Wednesday and Friday I'm traveling. So during that time, possibly I cannot schedule my class. So these are the 3 days. We'll anyhow go ahead. Right? If there are any queries from the previous session or something, we'll discuss them. Otherwise, I think we can move forward. Right? So if I remember correctly, we have actually completed the various aspects of feature selection. So we looked at the zero variance variables, removing the zero variance variables, near zero variance variables. If there are duplicated features, we wanted to remove them. If there are not duplicated features but are very highly correlated features, like -1 having a correlation of -1 and +1, then randomly one of those features, two features can very well be removed. Then similarly, if the correlation is very high, but definitely not a -1 or a +1, but it is either greater than 0.9 or less than -0.9, then we say you cannot typically remove randomly, right? Rather than that, form the groups of such variables. Form groups of such variables which are highly correlated. Let's say variable V1, V2, V3. These three variables pairwise, they are having a very high correlation. Let's assume that these three variables are having a very high correlation of greater than 0.9 between them. Right? Then what is being said? Form these three as a group. Similarly, if on the other hand you have V4 and V5, typically having 0.95 correlation between, -0.95 correlation between them. But V3 and V4, let's say, are having only 0.5 correlation between them. Right? So what we say, V4 and V5 is forming another group. Now what we do is, then a model is being, so what we say is, in this, from this group, only retain one and remove the remaining two. From this group also retain one and remove the remaining. Now, which one should be retained? For that, what we say is you take the target variable. In both the cases, you take the target variable and you build a model by taking these three as the predictor variables and this as the target variable. You build one model. Generally here, we build some kind of a tree-based model. So the most common model that is built here is a random forest model, though you can very well think of various other models. So don't bother about what is the random forest model now. But typically, a tree-based model is what is being built. And the most popular tree-based model is a random forest model. So we build a model by taking this as the target variable and these three as the feature variable. And the good thing about this random forest model is it gives an output called variable importance. It gives some output called variable importance. Now, what we say out of these three, so for each of the three variables, it will compute what is the importance of each of the variables in predicting the target variable. Right? So all the three variables, the same exercise happens. And based on that, the best out of the three is selected. The best out of the three is selected and the remaining two are knocked out. The same exercise happens with all the groups that you have identified. So from all the groups that you have identified, with every group, the best fitting variable would be shortlisted and all the other remaining variables will be removed from the model. So that is what we do when there is a high correlation between the variables. Let us see this exercise. Did we complete this exercise? Can someone update me? Did we complete this exercise of grouping the highly correlated variables and selecting only a few of them or something like that? Did we complete that exercise for grouping the variables and then selecting? No. Okay. So, but duplicate variables and the highly correlated variables of +1 and -1, we are done, if I am not wrong. Because that is what is my notes saying. We have done these activities by now, and I have stopped at this place, means this is something that is still going on. Okay. So if anyone has a question, you can post it. So probably it's like, okay. So let us quickly look at it. So yeah, this is the correlation. So we have seen that some of them have a +1 or a -1 kind of a correlation between them, right? So if there is a -1 kind of a correlation, what we are saying, we can set some kind of a threshold, let's say a 1 kind of a threshold, and identify if there are any columns which are having a correlation of +1 or -1. A4BA, what does that mean? Okay. Okay. So this is the variable which was having a +1 or a -1 correlation with some other variable. So if something is having a +1 or a -1 correlation, we can directly remove that variable. So because of that, we could see that the variable is directly dropped. So once I drop this variable business or commercial NOBC, initially it was there, but after dropping that, it would not be there. So which means once I have a gain, so I am dropping that from the column names. I'm also dropping it from the column values. So after that, when I have printed, I will not see that business. So whatever, what was the business or commercial NOBC, that variable would not be present, right? Then the next thing that we are saying is, look at those variables which are highly correlated, but definitely not a perfect correlation of +1 or -1. If it is a +1 or -1, you can randomly omit one of those variables. You don't need to do any big exercise, right? But if it is very, very much close to 1, but definitely not 1, you cannot randomly eliminate. You have to eliminate based on the best predictor for your dependent variable. So if you look at here, obviously I'm looking for those features which are having a correlation of 0.9. The point is here, there is no feature that is having a 0.9 and probably less than 1. So greater than 0.9 and less than 1, I'm not seeing any features now. So that means that probably there is no such activity here. But in the future, if you are working with some other data set, you need to be in a position to handle. So for that, what I generally suggest is, the first step is you take the correlation matrix. This is the correlation matrix, right? We have created the correlation matrix. This is the correlation matrix. So we have created by using the core function. So you take that correlation matrix, right? You first find out the correlation matrix and you stack up, take the absolute values of that correlation matrix. So here I am not much bothered about positive correlation or the negative correlation. So you take all of them and simply stack them. So rather than in a matrix format, put them in a stacking format, one above the other. So what does that mean? A matrix format is if the correlations are something like this. Right? If this is the correlation matrix, the stacking means it is actually becoming something like this. This is what is the stacking. I'll tell you why. This can actually help me to sort first of all. Once I stack it, I'll be able to, because it becomes everything in one column. So you could see that all correlations are shown in a kind of a columnar fashion, one single column. Then I can sort them in the descending order. So I'll basically come to know which pairs are highly correlated and which pairs are having a very low correlation between them. So you could see here in the data, there are some pairs which are having a correlation of 1, but they are all with themselves. But these are all the correlations with themselves. But after that, the maximum correlation that we are talking about is 0.85 only. Loan amount and property value are having a correlation of 0.859. But it is definitely not above 0.9. So that's the reason Nothing is getting identified at this stage, right? Probably if I said 0.85, then probably this could have come into the group. But because we have set it as 0.9, this pair is not coming up. But let's assume if I had put it as 0.85, then this pair would have come out. Loan amount and property value would have come out. If I had put 0.85, then it would be like a loan amount and property value would come into a pair. They both will be grouped together. I'm just giving parallelly the conceptual part of it as well. But right now, because we have set it as 0.9, even this pair is not coming into picture. Now, so we have setting anything greater than or equal to 0.9 but less than 1. So those pairs we are going to shortlist. So right now I can't shortlist. So right now it's an empty series because there is nothing that is having a correlation of greater than 0.9. So probably whichever are there, they will come in this kind. So I have created whatever with that correlation. Whatever is having a greater than 0.9 and less than 1, they would be shortlisted. And for them, the feature 1, feature 2 correlation value would be printed. So probably if this would have been the case, if I had said 0.85, then it would be like loan amount, property value 0.859. So like this, the table would be printed, even property value, loan amount 0.859. So these two would be printed like this. But right now, because we have set it at 0.9, it is showing an empty group. Then I am forming the groups of the correlated features. So whichever are having, so as a group, whichever are the ones that are having more than 0.9. So here there are only, where if I said 0.85, then it would be like my LA and PV will become one group. But with 0.9, nothing is forming any kind of a group. So that is where, how am I forming the groups? I am taking one by one because in a stack form. So I am taking every feature in feature 1. I am looking for which of these in the feature 2, the correlation is more than 0.9. So all those which are having a correlation of more than 0.9 with the feature 1, they all will be grouped along with the feature 1. And like that, the process is going to continue. Right? So here we don't have any such kind of groups. But had I gone with 0.85, then these two would have been as part of my one group. So right now for me, there is nothing to print in the group. Now, as I said, for each group, you do something called random forest classifier. We run something called random forest classification algorithm. So out of each group, I will take one important feature. So right now, my important features list is a blank list. But for each group, right, from each group, I will pick up one. So you could see here, I'm taking all the features from feature 1 and feature 2. Then I'm running something like a random forest classification algorithm. And I'm fitting it on the training data. And I'm finding out what is called as a feature importance. As I told you, the random forest algorithm has a very important feature called feature importance. So that feature importance will tell you within that group which variable is having a highest better relationship with the target variable. So those features will be appended and the remaining features will be discarded. So because we didn't have, so which means there a random forest model would have been created with my target variable and the loan amount and the PV being the two variables. Now the feature importance of LA and feature importance of PV, property value, both will be computed. So if this value comes out to be higher, then this variable will be retained and this variable will be knocked out from the data. Right? That is where we are saying. So you can very well see the features to consider. We are simply dropping out, we are removing from the total set of features which are duplicates or which are having high correlations. We are taking out the features that we are retaining. Remaining features are the ones that are going to be discarded. So in our case, there is nothing that is discarded because the original list itself was an empty list. We did not have any variables which were having a correlation of more than 0.9. But when you are working on some other data sets, this exercise will become very, very handy because you may come across so many variables which may have a very high internal correlation among them. So this entire activity, so once you know what are the features to discard, so you are just dropping those columns. But here in this case, I don't need to drop any. So my data is still lying with 38 columns. So I did not drop anything from my this thing. So which means this is one more exercise that we can very well do. Right. So this is the next feature selection exercise. Probably I don't want to use this one. Okay. So that is the one kind of a feature selection mechanism. So feature selection where, so this is the one more way I am reducing the size of the data. Reducing the size of the data by removing some of the variables which are highly correlated, but definitely not a +1 and -1 kind of a relationship. Any questions on this step? So this was our fifth aspect of selecting the feature variable. Then the last two that I am going to look at, one is called a mutual info based feature selection, and the last one is called F-test based feature selection. So these actually are primarily what they are doing is they will, again, these two are, they link each feature with the target. They link each feature with the target and identify those features which can play some role in differentiating the target. Some role in differentiating the target. So those variables are those features which literally do not have any role in differentiating the target variable. They would be directly omitted from the model. So that way, these two steps actually play a bigger role in reducing the size of the data set, in reducing the number of columns. So this is a very, very important step from that perspective because they focus a lot in terms of retaining only the important variables. Till now, if you remember or if you look at, right, we have taken some data set and we have been working on it, right? But we never look at whether these variables, these are so many variables that I had, whether these variables are going to impact my target variable or not. Are they just there for the sake of being there? Or are they going to impact my target variable in some way or the other? So that is a very important thing. Otherwise, it becomes a garbage in, garbage out kind of a scenario. We have so many variables because we collected a huge data. Lot of our databases were filled with so much of information, and I have taken all that entire information. I never checked whether this column is useful to predict the target or not. What is the relationship between the target variable and that particular column? I never looked at it till now. Now, this is where these two measures, they literally play an important role, right? These two measures, they play an important role. And based on that role, you will find that so that is where you can clearly see which variables are important and which variables are unimportant. Now, out of this, the mutual info based method is typically a non-parametric method. It uses the concepts of joint probability to the individual probabilities ratios, right? To identify what is the impact of that particular variable on the target variable. So generally what it does is it looks at the probability of X and Y occurring together, right? And it could also look at individually the probability of X and Y. And the logarithm of this is being taken. And this is again multiplied by the joint probability of X and Y. So this is what, and it is summed up across all the possible occurrences. Now, this is what is a typical way. You don't need to bother about it. But one simple thing that we can see is the mutual info wise, there is a kind of a minus also in between. So if X and Y are completely independent, right? If completely independent, obviously probability of X intersection Y is going to be the multiplication of these two. The logarithm of this is log 1 is going to be 0. So the entire value would be coming more closer to 0. Whereas if X and Y are having some level of dependency, you will find this numerator to be lesser than the denominator. So the logarithm will be a negative value. Negative times negative is going to be a positive value. So if the mutual information value comes out to be 0, you can say that X and Y are very much independent, which means that particular variable X does not influence Y. So probably you can directly remove that X from our model. Whereas the higher the mutual information value, so we can very well say that the dependency of one on the other is very high, or the kind of mutual information that they are carrying is very high, which means those variables can very well be retained because they have some information which can help us in predicting the Y's. So that is how you can look at the mutual information. Similarly, when I am doing an F test, The F test is typically performed by using an ANOVA model. Again, the same, if the F test, so for the F test also, I can, because it's a statistical test, I can compute the system will give me the P value for the test, because the ANOVA model is simply saying there is not much of a significant difference between the two groups in terms of the other variable that is there. So here we are talking of two groups as the defaulted and the non-defaulted groups. So I can very well see the distribution of the other variables across the default, because we have already converted all the variables if they are binary, if they are categorical also, we have already done a variable encoding, categorical variable encoding. So basically what the ANOVA model is going to do here, or the F test is going to do here, is look at the various groups, and based on the groups, what is the distribution of the X and Y. So if the distribution is more or less uniform, then the P value will be very, very high. But if the distribution is very different between the defaulters and the non-defaulters, the P value will go much lower. Let's say less than 0.05. Right? So because here the null hypothesis is there is no difference across the groups, whereas the alternate hypothesis says there is a significant difference across the group. So the moment I am getting a significant difference, then that particular variable will become an important variable to be retained. Whereas if the significant difference is not existing, then I can very well drop off that particular variable as well. So in this stage, if I once I do these two steps, these two kinds of tests, what we will end up seeing is the problem size will come down quite drastically, and only those variables that are in some way or the other, at least minutely, I'm not talking of very significantly also here, at least minutely they are impacting my target variable. So at least minutely, if they are impacting the target variable, those variables will be retained and all other variables can be removed altogether. All right. Now let us implement those two. So feature selection based on mutual information. So because this is a classification problem, I will look at mutual info classification. If it is for a regression problem at a later point, we'll look at this part. And so we'll use the mutual info, and probably we can select the K best or K percentile, or sometimes forget about K best, K percentile. If the mutual info is just around 0, drop it. So what is that I'm doing? I'm running this function called mutual info classification with the training data. So I'm giving the training X values and training Y value. And here it requires the Y value has to be an integer. So anyhow, we have converted it into 0 and 1. So it was a dummy variable, but in case it is not a dummy variable, probably you can make it as an integer by doing this hash type int. So this gives me all the MI values. So you could clearly see here, I'm converting it into a MI values, and I am also taking the names of the columns. And so because I wanted an index, now we have sorted all those values, and we are simply plotting them. Because we have done an in-place sorting, the order has got rearranged altogether. Now I could see that Some of them are having a very high mutual info value. Probably loan to value ratio is having a very high info value. It's not very high, basically. It is still 0.0175. So generally what we say is it should be at least 0.001 or 0.002. So anything that is still above 0.001 or 0.002, at least some minimal information is existing. I mean, we can get the info values to almost 0.4, 0.5 also in some of the problems. So here we got even the best one is having a very small mutual info value, so which is also a kind of an indicator that probably the information that is present in all these variables is also very limited with respect to the default of the person. Okay, so loan to value ratio looks like an important variable, followed by property value, loan amount, and so on. But after a specific this thing, I see that almost all these are carrying an info value of almost 0. So which means these variables are completely independent when I am putting them against y. So which means without any further thought, they may be good variables when I have collected, but when we are working on the data, we are seeing that these variables are literally useless. So all these variables, right from loan purpose P4 till the last, all of them can directly be knocked out. Now you could see here, I've just got the numbers. The highest is loan to value ratio, 0.018, and it has been reducing. Generally, what we can say is anything from here, I can knock it out, because generally I'll put it like 0.001 or 0.002. So this is very close to 0.002. So probably I may want to retain, but all these things definitely I can knock them out. So that way, my problem is becoming a very simplified problem. Earlier, there were 38 columns in that problem. Now, suddenly, so many, how many? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, 20 columns are getting dropped out. Out of the 38, almost 20 columns are getting dropped out. Now, that way, your overall problem size is going to come down. So, let's say I have set anything greater than 0.001, they should be retained. So all these will be or even this would be retained, right? Anything greater than 0.001 would be retained, means all these will be knocked out. So the moment you could see only 18 or 19 variables are left after this knockout. So which means you again readjust your data now. Your data now, both the training data and the testing data are becoming reduced only to these 18 or 19 columns. From 38, they have fallen down. On the similar note, you can also use the F-test also on the filtered data, because I don't want any variables which are really useless, because it looks like they are there, but obviously they will not give us any better result when we are using them in the model. So here also you could see I am running a F classification test by giving the training data's X values and training data's Y value. X values are your predictor variables. Y values are your target variables. So here it gives me the coefficients, the F-test coefficients and F-test p-values. Now you could see here all these p-values are greater than 0.05. So wherever the p-value, less than 0.05. So if the p-values are less than 0.05, you can retain. So this is also 0.01. So the variable is still an important variable. But you could see this one, It is 0.5, which is greater than 0.05. Now here I will knock out this variable. Even this one, 0.5, knock it out. 0.04, retain it. 0.95, knock it out. 0.45, knock it out. 0.39, knock it out. So it looks like there are so many variables that are getting knocked out even through the F test. So once these two things are being done, so you could see here, the p-values when we are plotting, all these are approximately 0 in the p-value. But after that, the p-values are increasing, and probably they have gone to 0.8 and 0.9. So these variables, definitely anything greater than 0.05, just knock them out. So retain only those variables whose p-values are less than 0.05. So overall, what is happening if you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 variables are left. All the other variables are knocked out. Only 10 variables are remaining. So it looks like income, submission of the application to the institution, property value, the debt to income ratio, negative amortization, whether it is yes or no, loan amount, loan to value ratio, whether it's a joint account or not. So it is hardly mattering whether the person is a male or a female or gender not mentioned. All those three are of one category, but probably the joint gender is looking like a separate category. Joint gender here is nothing but the joint, what you call the joint gender here is nothing but the joint account holders, right? Then we can talk about the term and the age. Age between 55 to 64 is slightly different from all the other ages. So which means all the other ages got grouped now because of this removal. Only the 55 to 64 is coming out as a slightly significant variable. So that is what is the scenario as of now. Only those 10 variables are there, which means my model has, my data has become a very, very simplified kind of a data. So probably, I don't know if I have reworked somewhere here and there. So when I run it again from the scratch, probably if there has been any duplicate work or something, they would get addressed. But for the time being, you can think of it like these are the only 10 columns that are more important for this model, and all the other values are simply knocked out. So just let me know, because we are almost coming to the end of the data pre-processing. So from where I think we will be starting off with the building of the model. Now this will be the data set which we'll be using for building our model. This will be the data set that we'll be using to build our model. So probably if anyone is having any kind of queries on any of the gray areas, I think I'll spend some time, because this PCA right now, I don't want to address it. Right? It's not an important step at this moment, right? When I discuss about the unsupervised learning, probably at a later point, only these 3 or 4 blocks, right? Only these 3 or 4 blocks you can say. The PCA is only associated with these 5 blocks. So these 5 blocks I will explain you at a later point. They are not showstoppers also, but at the same time, once we discuss about the PCA in detail, I'll again come back to this. Okay, so these 5 blocks, if you want to hash them out for time being, we will hash them out, so that if you are running end to end also, it would not impact, right? So that even if you are doing end-to-end execution, of course, even if it is there also, it will not impact because I have created a separate variable for that. So it will definitely not impact your major flow, right? It would not be and it would be an unutilized kind of a component because I have segregated this. So anyhow, I'm keeping it like this. Though it will execute, it will not have any impact because if you see the next step is not done on the PCA, it is done on the original data itself. So anyone having any kind of questions, I would pause here, or probably the last step in the process is you try to do a scaling of the variables also, because scaling, we have already discussed about different forms of scaling, right? Different forms of scaling are nothing but you can do a kind of a set score kind of a scaling, which is called standardized scaling, where you subtract each observation, the mean, and divide it by the standard deviation. Or I can also do what is called as a min-max scaling, wherein I would subtract the minimum values of that particular column and I divide it by the range of that particular column. So that is what will set the values to lie between 0 to 1. So in this case, you will have all the columns with a mean of 0 and a standard deviation of 1. So we are almost like standardizing all the columns because there are a couple of advantages which we have already discussed earlier. I don't want to repeat them. You can refer to the notes and the videos associated with that particular aspect. So once we do that activity also, we are ready to build our model. So we are going to start with what is called as a basic perceptron model. So because we are getting into the modeling part, the machine learning models. Now this is where we are going to start with the various machine learning models. The good thing is the framework is the same for all the models, right? So the thing is, if you know the mathematics, it would be good. It would be good only. If you don't know it, it's still fine because from a business perspective, you can run all the models because all of them follow the same framework. And the whole thing is being built by using only one library called scikit-learn. So scikit-learn is a very, very excellent framework to run few hundreds of machine learning models. Right? So that way, many a times what happens is, even if I don't know what is the mathematics behind each of the models, does not matter because I'll get the output and the interpretation is also more or less unique. So we'll see that, right? Because here the objective is more on a practitioner's perspective. But at the same time, wherever applicable and wherever very, very important conceptual aspects or mathematical aspects are required, I'm going to cover them as well. But where very advanced mathematics comes in, I will just let you know that we can contact separately, or we will plan it out. Right? You can read through it separately, or we can have a separate discussion on that. Because I don't want to intensify the mathematics as a part of this course. Wherever required, I'm going to use. Wherever some simple applications of calculus, simple applications of equations and all are there, I'm going to cover that. Especially, let's say, if I want to do a logistic regression, I'll derive something for a logistic regression. If I want to talk about the decision trees or random forests, the mathematics behind that, I'm going to look at it. So some of these aspects, definitely we are going to look at from the mathematics perspective as well. So I'm just waiting for any queries before we get started with our models. I want to pause for a couple of minutes on the clarity part, something that needs a kind of a repetition or some such kind of thing. I don't mind spending some time because this becomes the most crucial aspect before building any models. Building a model is one of the easiest things in the entire machine learning exercise. In the entire world of data science, building a model is always treated as one of the easiest steps, right? But bringing the data to be in such a way that it can be modeled quite comfortably with a very least amount of effort, that becomes the most challenging thing also, as such. Is there any gray area that came up? Was I too fast? Or is it like it's going fine? Hello, am I audible? Okay, okay. So, I mean, I was just wondering because no one was trying to come out with any kind of queries. So I was not clear whether whether we are all going fine or something got as an obstruction or something like that. Can we have the next model with insurance data? Yeah, you can actually do that exercise, right? So you can do one thing, Vigneshwari. I can give you some claim default or we have claimed the insurance claim related data. I can share one data set with insurance claim related data. What you can, so we can have an insurance claim related data. Okay. So you can do all the activity that we have done till now, get the data to a stage where we can apply a model on it. So it is exactly the same thing. What I would suggest now, we have done so many steps. Let me tell you, any data that you bring in, now the kind of framework that we have created, I want all of you to test this framework, right? Because this has been created with a lot of iterations, with many iterations going on. So you can very well try to test this framework, right? By taking some other data set and try to see in how much time you are able to reach to this level. To a large extent, my personal feeling is reaching to this level on a new data set should not take more than a couple of hours. Right? That too when the data set is very large. Otherwise, you should be in a position to reach to this level in a few minutes. So you take up one data set, let's say, which is having 1,000 or 2,000 rows of data. Follow my entire code step by step. Without error, you should reach this step. Once you reach it, the models are simply following. So I am very much sure we'll work it out on a one-on-one basis or probably in smaller groups. But what I suggest is you take up some data sets. There are large number of data sets that are available on Kaggle. So you simply visit kaggle.com. You can search on insurance or something, right? Or if you are fine, I can share one or two data sets with you along with the problem. But you have to come forward to apply exactly whatever we have discussed. This case study is a very, very beautiful case study according to me, though I have developed it. I am very, very convinced that it can be used in commercial assignments also, because all the steps have been taken care of into it. There could be a one or two deviations here and there, but majorly it looks like I have taken into consideration all the steps. So that's the reason what I suggest to test the robustness of this entire framework. I suggest that you can take another data set in parallel. So you take insurance, someone else may take credit card, someone else may take probably from the world of marketing. Doesn't matter, right? So probably, yeah, that's a good idea. If you want to form smaller groups also, that would be much better, right? So it hardly matters, because as a data scientist, once I am getting into working with the data, it hardly matters whether I am working with banking data or an insurance data or anything, because yeah, the domain knowledge is one advantage that I need to have. But once the data is there in place, I have to purely be driven by all these kinds of relationships, etc. So that's the reason I suggest that you can take. I mean, for the regression, I would be taking the insurance data only. But for classification, I would be going with this data only. Right? I mean, I don't want to change the data set for the classification model because we have representations from across. But regression model, I'll still take up the insurance related data. But you have all the flexibility to work out. So if you say you can't get the data set, I don't mind giving a data set and asking you to work out. If you are all willing to work on it, I can share one insurance data set and I can very well ask you to work out on it. Would that be a good idea? Yeah, I'll share the data set today itself. Okay, so your job is try to work out on the code in such a way that you are able to bring the data to the modeling state. Right, all preparations, and wherever you are getting stuck, you just let me know. Probably if that requires a modification to my own code, I can very well do that. Yeah, how about others? Feedback and opinion from others. We are entering into the modeling phase. Any areas of concern, etc., just let me know. All right, then I'll move to the next. Okay, so we will start. Okay, I'll suggest a few data sets. I'll upload the data sets today. Right, I'll tell you what is the variable. So they may or may not be all from the insurance, but definitely I'll pick up something from the BFSI domain. Right, because at the end of the day, we all should be comfortable in terms of picking up any data set and doing all these activities on the data set and probably run a model and try to see. Sometimes this entire process can be automated also, right? So yeah, from that perspective, yeah, I'll suggest 2 or 3 data sets which can be helpful. So they will be from the BFSI domain, but definitely are not necessarily from the insurance space as such. And if you are comfortable, you can pick from the other spaces also. Why only? At the end of the day, any problem, right? Where keeping aside the domain knowledge, right? So the domain knowledge is not something that we are learning in this particular program. So everyone will have domain knowledge in his or her own areas. So keeping that domain knowledge aside, I want all of you to be comfortable with handling the data. Given a data set, all of you should be comfortable handling the data and trying to build models and do the interpretations, etc. So that is the prime objective of this entire data science course. So wherever you come across a data, you should start thinking, and that too there is a kind of a categorical variable that can be predicted. You should start thinking, can I build, am I comfortable in building a classification model? So basically our focus should be in terms of solving a classification problem with higher levels of accuracy. All right. So the focus is on data cleaning, data preparation, feature selection, feature engineering. And now we are coming to the penultimate step, which is the model building step. All right. So right now we will focus on classification models. But once we are done with the classification models over the next few sessions, then we will move on to the regression. So there are 2 types of predictions here, so which fall under the supervised learning category. One of them is called the classification problem. The other one is called as the regression problem. So we are getting started with the classification problem. So in the regression, we did a linear regression earlier, right? We have already done the linear regression earlier. And we talked about ridge and lasso, elastic net kind of regularization frameworks as well, right? So we will look at a series of classification problems, and then we will again revisit some additional regression problems. So the first of this is a very basic problem called basic perceptron. This is actually, it's a very basic thing to start with, but this one has actually led to the most powerful concepts called artificial neural networks. And from where it has also gone to the same concept is applied in deep neural networks or deep learning kind of mechanics. But what we are going to learn is a very, very basic perceptron now. I mean, we will talk about an introduction to artificial neural networks and deep learning, probably after a few sessions. But here we are going to touch base upon the very basic element called basic perceptron. Now, what is happening? The way. Now here we have to talk about every model. Now for every model, for every algorithm, there are some commonalities. There are some commonalities that we have to understand. Every algorithm is about some kind of relationship between Y and X. Y, as you all know, is your target variable. X is your feature variables. So for every algorithm, we are trying to build some kind of relationship between F and Y and X. So this is what we are typically calling as a kind of a learning. So y, the relationship between y and some function of x's is a kind of learning or is a kind of generalization that is happening. So generalization, or sometimes we use the word abstraction, is typically the learning. X is the actual data, right? And typically the relationship between y and x is happening through some function. The relationship between y and x is happening through some function, and that function is what we are calling as a learning function. That function is what is actually doing the learning part. Okay. So how do I assess the goodness of the learning? So there is some learning. So there should be some way that I should assess the goodness of the learning. So from there, what is that we are saying? There is an error function. So obviously, there is the actual y that is existing, and the f of x is actually leading to a predicted value of y. So there is an actual y, there is a predicted value of y. So there should be some kind of discrepancies between the two. So there is some way the error has to be measured between them. Right? There has to be some form of error that is measured. Now, based on this error, there can be a kind of go back. Right? Go back and rework on the function. Rework on the function in such a way that the overall error is minimized. So if you want, you work it again and again and again, multiple iterations, so that finally the overall error is reduced. Now that is what happens in every machine learning, because there is a learning and there is a loop. So what is happening in almost all the algorithms? Initially my x's are taken. X's are my features. Right? What is happening if we look at this is what is the world of machine learning. Initially, I have my features, or sometimes you can call them as inputs. Now, these inputs, some function is applied on these inputs, and some output is computed. Some function is applied on these inputs, and some output is computed. Now, this output is compared with the actual output. So this is my predicted output. This is my actual output. So obviously, when these two combine, there is some error that is coming up, because obviously my predicted and actuals will not match. So the error is coming up. Now what is happening? This error is actually helping me to backtrack. Based on this error, this function is again re-updated or updated. So this function is updated again. Now, when this function is updated, obviously again a new values of this come up. And again some new error comes up. Again it goes back. So it goes into a kind of a loop. So this learning is happening in the form of a loop until this overall error is minimized. So because the number of iterations that are happening, we do not have a control on the number of iterations that can happen. Right? We do not have any control on the number of iterations that can happen, because until the error goes down lower and lower, this process keeps on iterating. And that is where we say the system is learning. So initially it has started off with some function, it has given some output, but while comparing that output with the actual, so some additional insights have come. So it is looking backward. It is trying to analyze its own learning, make improvisations to its learning, and again redo the entire activity. So that is where we call this kind of a thing as there is a feedback that comes in. Feedback is nothing but the error is coming in the form of a feedback. So by using that feedback, there is a learning that is happening and the updation of the weights is happening accordingly. So that is what is the common process to every algorithm. So what we will be learning in the whole process is, one is what is the function that is binding the x and y, what is the cost function, or the probably we'll call it error function, what is the way in which the error is measured, and how is the feedback maintained. How is the feedback resulting in updation? These are the only things. If we are clear on these aspects, any model can be done quite comfortably. All right. So now I will come on to this model called basic perceptron. Now the way the basic perceptron works is quite simple. Let's say we have our input variables. These are our input variables. Now, all these input variables are joined, right? There could be a weightage of W1, W2, W3, Wn. Error function is always in same calculation or keep changing depending on the function has been chosen. No, error functions, there are majorly 2 or 3 different kinds of error functions, though you can use more. So, but generally what we see is for classification, all classification problems, we generally go with one kind of error function. And for all regression related problems, we go with one kind of error function. You can very well change them also, right? But that's the most common way the industry looks at. So it is not depending on the function that we have used. To a large extent, it is based on the kind of model that we are, the kind of problem that we are using. So for all the classification related problems, I'm going to use the same error function, except for this basic perceptron. After that, whatever are the models that we are going to use, I'm going to talk about. I mean, I'll tell you why I have not used. So why what error function is being used? I'll talk about it. But yeah, so just hold on to that. But yeah, to answer your question, more or less it is the same. Only 2 or 3 variants are there. So if you already remember when we did the linear regression problem earlier, we talked about the ordinary least squares. So that is what is our probably mean squared error. And if you remember, we have set our error function. We have set our error function as we have set this as our error function, right? This is something that we have set as our error function in case of a regression problem. This error is generally our mean squared error, right? So there are some advantages of setting this because most of the times what we work on is we work on something called a gradient descent. We discussed about this earlier, right? So again, I'm going to discuss them. Gradient descent is nothing but a kind of a reduction based on the slope. So if I really look at the, I mean, if I am really looking at the variables and the parameters, normally in a typical way, you will reduce the slope to zero. You will equate the slope to zero. Whereas when we are doing it the computer way, you will keep reducing the slope by a small factor. So the slope of this particular function, the reason why it becomes easier to choose this kind of error function is, if I take the derivative of this, obviously it becomes 1 by 2m into 2 into sigma I equal to 1 to m yi minus of a plus bxi times xi. So this is actually becoming 1 by m times, which is like an average, I equal to 1 to m. So this is simply becoming yi minus y cap, right? So which means this multiplied by this. So basically this is nothing but the error, and this is nothing but your x value, which is the your feature variable. So what is happening, instead of directly equating it to zero, because that requires a solving. Now what will we do? We take this, we multiply this with, so this is easier to do. So because I know the error already, I know the x value, I multiply this with some small learning rate. And that's how I decrease my weights. So my b dash will become b minus whatever is the error that I got in this iteration times xi times alpha. So that would become my new b dash. So again, similarly for a also, it becomes more easier, right? If I am so by taking this kind of an error function, the advantage that comes is this is differentiable. And once it is differentiable also, I'm able to get it as a generalized kind. Now I don't need to do differentiation every time. It's a kind of a simple generalization. Error that is there, that is multiplied by xi, and you take a small learning rate, and by that extent you reduce. So you are using the gradient, which is what is called as the slope. You are reducing, you are actually moving in a direction where your error is actually coming down. Rather than randomly making your moves, you will make your moves in a streamlined fashion, which is called as your gradient descent based movement. All right. But here again, let me come back to this. So basic perceptron works like this. You have x1, x2, x3, xn. So there are some weights W1, W2, W3, Wn. So initially, these are random. There is no basis for the selection of weights. So initially, they are all random. So after that, all these are combined into a sigma function. Sigma is, it becomes W1x1 plus W2x2 plus and so on, Wn(xn). So that is what is the sigma that is applied. So there could also be a constant term 1, which is having a weight of W0 also. So sometimes people call this as X0 also. X0 is nothing but 1. Okay, so basically that becomes the interceptor W0 plus this. Okay, because the X0 is 1, so I can very well write it that way also. So based on these, if I remember or if I tell you correctly, these X1, X2, X3, you could see that they could be positive and negative values also, because if you look at the code, we have already done a kind of a standard scaling with them. And because we have done a standard scaling, you see positive as well as negative values in the data. So once I do this output, right, this output is passed on to a function called an activation function. This output is passed on to an activation function. In this case, the activation function, because it's a very basic thing, the activation function is a step function. I'm not writing the mathematical notations everywhere. So in this case, the activation function is a step function. Step function is nothing but the rule that the step function applies is, right? Let's say this is typically called g of x. So what we are saying is, if the g of x is positive, or if it is less than 0, the output will come out as 0. If g of x is greater than 0, the output is coming out as 1. So the output out of this process will be either, so this would be treated as your y hat. So the output of this process is going to be y hat. So this y hat is either 0 or 1. So then this is compared with your actual y. So there is a y hat, there is a y, right? So here the y hat is always 0 or 1. Y is also either a 0 or a 1. So the normal possibilities are, there are 4 possibilities only that can come. Both are ones, 1 and 0, 0 and 1, 0 and 0. So if I look at the error, if both are there, the error is anyhow 0. If both are 0 also, the error is 0. If both are 1, now here, the error is typically taken as the mean squared error only. The error is taken as the mean squared error only. So in both these cases, the error is going to be 1. Now, as per the rule, what should happen? It has to go back and it has to update the weights. Now we have got the error. The error is what we are calling as the mean squared error. Or even if I say, if I go with yi minus yi cap, right? In this case, it would be -1, and in this case, it would be 1. So in the basic perceptron, what happens is, you would take your weights. Let's say now I want an updation of my weights, W1, W2, W3, Wn. So in this case, what can also happen is, my old W1 minus whatever the error is there. Now here, the error could be taken on a one-on-one kind of a basis. Means for the first row, what is the error? Then that would be applied to the second row, third row. Or sometimes it could be a kind of a pooling of all the errors. So summation of all the errors. There could be a summation of all the errors. So what could very well happen? I can very well look at whatever is the error, and I will multiply it with xi. That error, I'll multiply it with xi. And here I'll not use a learning rate. That is because it's a very basic model. The learning rate by default is taken as 1. So what is happening is my weights are getting updated like this. My weights are getting updated like this. And once this process is updated, again the W1x1 plus W2x2, W3x3, that is done. This step comes, this step comes, this step comes. Again, there is a kind of an improvise. So the process keeps on going. But because here the learning rate is not there, right? What we generally observe in a perceptron problem is it is very, very difficult for the solution to converge. When the alpha values are very small, we see that though the system takes a slightly longer time for building the model, but we always observe that the solution can converge. Whereas in a basic perceptron, that cannot happen because the alpha value is 1. And because of that, huge modifications to the weights are going to happen. So the weights are going to change quite drastically. And if the weights are changing quite drastically, what you will typically observe is, so you will have to take the average error because you have a 1 by m also coming up. So whatever is the error, you can take the average error, and that average error is multiplied by your xi. So you will find that the wi's are going to change wi's are going to fluctuate quite drastically. And because of that, the convergence to a solution is a very, very difficult exercise when it comes to this basic perceptron. But this basic perceptron needs to be understood a lot because this is the one that is going to give way for various other models as well. Right? So here the error function is still your mean squared error only because the output that comes out of this exercise is going to be a 1 or a 0 kind of an output because it uses a step function. Because of that step function, the output is a hardcore 1 or a 0, nothing in between. And because of that reason, a direct comparison can very well happen, and which in a way can typically work well if we are using an error. If we are using a kind of an error function, which is a mean squared error kind of a function itself. All right. So any questions on that? Probably we'll quickly execute the model and we will see. So for that, okay, these are the steps. Initially, you can import. So this is a linear model. Very basic. We have seen W1, X1, W2, X2 kind of thing. So it's a linear model. From the linear model, we import something called perceptron. Similarly, the other models also will be imported like this. There are a lot of metrics that we are going to discuss. So I'm importing all those metrics. Right, when I execute them, we'll discuss. I don't think today we will discuss those metrics, but one or two metrics we'll look at. Right, there is an accuracy score, balanced accuracy score. There is a classification report, Cohen's kappa, confusion matrix, F1 score, precision recall. So there are so many such kind of metrics that we are going to talk. Now, what is that we can typically do? First, you initiate the perceptron model, any model. So right now we are talking about basic perceptron, so you initiate the perceptron. Tomorrow when you do logistic regression, you initiate the logistic regression. Day after tomorrow when you are going to do random forest, you initiate the basic model with the basic set of arguments to that model. Then go ahead fitting the model on the training data. Go ahead fitting the model on a training data. So a few models, they can display the coefficients, especially the linear models, and a few non-linear models, they can display the coefficient. So you could clearly see here, the first one is for the constant, and probably after that, the 9 coefficients that we are talking of, they are associated with the 9 variables. Okay, there are 10 variables. So this one is not there. The intercept is not there. So basically it looks like minus 2.87 times income, 0.53 times submission of application, then 2.43 times the property value, minus 0.06 times the debt to income ratio, and so on. So that is how you can look at, which means some of the variables are negatively impacting. So you could see if I go with that, the higher the income. So if I look at the coefficients, the negative coefficient here means higher the value. So which means higher the income, the lesser is the probability of 1. 1 is nothing but default. Lesser is the chance of default. So lesser is the default, because default is treated as 1 and non-default is treated as 0. So what we are simply saying is, if the income is higher, lesser is the chance of default. Similarly, here it's a positive relation. So which means if the submission of the application to the institution is there, then probably the probability, the default chances are increased. The higher the property value, this is a positive relation. Higher the property value, the higher is towards the default. Whereas the next value is the debt to income ratio. The higher the debt to income ratio, lower is the default. Now something is not wrong, something is wrong here. Right? I mean, wrong means possibly some variables are overlapping onto each other. Right? Loan amount is positive. The higher the loan amount, then the higher the chance of default. Similarly, loan to value ratio is also showing with a very high positive coefficient, which means it's one of the most important variables. Joint account, so someone who is having a joint account, their chances of default are lower because there's a negative relation. And the term also, probably the longer the term or tenure of the loan, the chance of default is lower. And the last one looks like age, which is looking like a positive thing. So people with 55 to 64 kind of an age group, the defaults are happening in larger numbers. So, but our interpretation is, our intention is not in terms of interpretation here. So we are done. So basically the first step is we have gone with the default model, initiated the model, we fit that model. Then we look at coefficient. This coefficient will not be applicable to all the models. Then we talk about scoring this model back on the same data. So it's like we build a model on the training data only. We build a model on the trained data. So whatever the model that comes, this model is again tested back on the same data. This model is again tested back on the same data. Now, why is it tested back on the same data? For that, there is a very simple explanation. And probably one of the problems that we are trying to overcome here is the underfitting problem. By doing this, we are verifying whether the model is underfitting or not. How we can verify? If I built a model and I did not test on the new data, I am testing it back on the same data itself, right? So what we say is, when I am testing the model back on the same data, if the accuracy is lower and lower, then the model can be scrapped altogether, right? It is not able to reproduce the learning. It is not even able to reproduce the learning. Forget about the learning. It is not able to reproduce on the same data itself. Forget about the new data. So in that case, probably we say that the model is, where we can very well say that the model is underfitted, right? So what are we saying for that? How do I compare that? I will score it again back on the training data. So let's say I have got 73.72% accuracy. Right? I'm getting 73.72% accuracy. Now, what is that I can very well do? I can very well look at what is the default accuracy or null accuracy. What is this null accuracy altogether? What we are saying as null accuracy is, you look at in the data by default, there are 2,375 non-defaulters and 453 defaulters. That is what is my data composition. Right? My data composition is containing 2,375 non-defaulters and 453 defaulters. So approximately 83% of the, or 84% of the people are non-defaulters. Now, what are we saying? When 84% of the people are non-defaulters and only 16% of the people are defaulters, it could very well be possible. I don't build any model. Forget about any model or anything. Right? Forget about any model building or any of the activities. Blindly classify everyone as non-default. You are getting it? Blindly classify everyone as the majority group. So because the majority group is 0, which is non-defaulter, what I'm saying is I'll classify everyone. I'll not build any model, anything. I'll say no one will default. That is my prediction. My prediction is no one will default. So even in that case, my accuracy will be 84%, because I'm saying no one will default. In reality, 84% of the people did not default. So at least in 84% of the cases, my prediction was right. So my accuracy is around 84%. Right? But by building a model and then testing it, my accuracy is only 73% or 74%. So which means my model did not do any good job. My model has actually underperformed because the default accuracy itself is 84%. So anything that my model is building, it should actually generate an accuracy of above 84%, but it has gone into 74%. So probably we say this model is underfitted model. This model is suffering from an underfitting problem, or the bias is much higher here. So we may have to look out for a slightly better model. But definitely, so that is why we do this exercise. We score it on the training data, score the model on the training data, and we try to look out for the accuracy of the same. So once I get convinced, right now I did not get convinced, but again, this is a very generic model that I'm talking about. That's the reason. In case I get convinced that this is a good model, it does not suffer from under fitting bias, then I'll fit it on the testing data. And once I fit on the test data, I can see here, right? In my actual test data, I'm seeing 85% of the observations are non-default, and only around 15% of the observations are default. I will compare the accuracies. So there are a hell a lot of metrics here, right? And this kind of a table is called as a confusion matrix. So this 4-block table is typically called as a confusion matrix. And based on this confusion matrix, we will compute a lot of, this confusion matrix is what will become the key. So the confusion matrix is nothing but, I'll just give a basic overview of the confusion matrix. The details of the confusion matrix we will take up in our tomorrow's session. So basically it creates a 4-cell block. There are predicted values, and this side we talk about actual values. So predicted could be 0 and 1. The actual also could be 0 and 1. So these 4 blocks are actually named something. So generally 1 is called as positive because it's an event. 1 is always associated with an event. Default, claim, bankrupt. So these are some of the events occurring. So 1 is always associated with a positive. 0 is always associated with a negative. So 0 is associated with a negative. 1 is associated with a positive. Now these 4 columns, this column is called as, okay, from the prediction perspective, look at it. So the prediction here for this column is negative. The prediction that was done for this column is negative. The prediction that was done for this particular cell is positive. The prediction done for this cell is negative. The prediction done for this cell is positive. Now, this negative, actually, is it true? Is it negative itself? Yes. So because of that, this is called true negative. Now, this is positive. The prediction is positive, but actually it is negative. So which means it is called false positive. Now here the prediction is negative, but actually it is positive. So this is called false negative. The prediction is positive, actually it is positive. So this is called true positive. So these are the 4 cells that typically come up. So in our case, we are seeing 866 true negatives are there in the testing data. 167 false positives are there. 131 false negatives are there, and around 48 true positives are there. So overall, if I really look at probably adding up row wise and column wise, So I see 997 predicted as negative altogether, and probably 215 are predicted as positive. So predictions wise, 997 are predicted as negative, 215 are predicted as positive. Whereas in the actual data, 1033, 866 plus 167. So 1033 are negative, and probably only 179 are positive. So this is the basic this thing. Based on this, we get a lot of other metrics. So I'll not look at those metrics right now. We will look at those metrics probably in our next session, which is tomorrow, right? But until here, if anyone is having any kind of questions, we can very well discuss them. Otherwise, I'll stop the session here, because the most important aspect of various metrics and all